Okay, so let's do another example on the same case, distinct real eigenvalues. So the matrix is 1, 3, 3, 1 for the system. So remember, either go by the way you learn in linear algebra, pull out lambda from the main diagonal, or as I recommend, remember the shortcut, this leads to lambda squared minus the trace, which is 2, plus the determinant, which is 1 minus 9, that's minus 8, right? So the determinant is minus 8, so therefore that's the characteristic equation. This also factors nicely into, let's write it here, into lambda minus 4, lambda plus 2 equals 0. Okay, so if you set up each equal to 0, you get lambda 1 equals 4, the first eigenvalue, and then the second eigenvalue minus 2. So when you look at the formula sheet, keep in mind that this is what indicates the case you are in, because there are 3 cases in total, right? Depending on the types of roots you have for lambda. So eigenvector now, let's try to do this a little bit faster than before. So lambda 1 equals 4. I'm going to subtract 4 from the main diagonal. With a little practice, you could do this very fast. The extraction of the eigenvector in the 2x2 case is very easy once you get the hang of it with the whole mechanics. So first row becomes minus 3, 3, 3 minus 3. Like for example, with a little practice, just by staring at the system here, I can tell that the eigenvector is 1, 1. The reason I can tell is because I can see that if I do the equation minus 3v1 plus 3v2 equals 0, I can realize in my mind that that means 3v1 equals 3v2. So the eigenvector states that the 2 row entries are equal to each other. v1 equals v2. Now what's the easiest possible non-zero vector? 1, 1. Minus 1, 2, 2, 4, 4, whatever, right? Any vector with equal entries, any non-zero vectors with equal entries will be my eigenvector. So doesn't matter which one you pick, these are dependent rows. So minus 3v1 plus 3v2 equals 0. Just plug in 1 for v1, solve for v2, and you'll see that v2 is equal to 1 as well. Right, so try to do this, especially in cases like this, try to do this in your mind after you practice enough, not before. I mean, we're not, you don't have to rush until, don't go faster until you're comfortable with the whole thing. So v1 is 1, 1, lambda 1 equals 4, right? So remember these two come together in the solution. These form one independent solution. So let's continue with the second eigenvalue. Lambda 2 equals minus 2. Again, very carefully pull out minus 2 from the main diagonal. So we have a double negative there. And 0, 0 on the right hand side. Okay, so the matrix is now 3, 3, 3, and 3. So again, if you practice quite enough, you should probably tell right away out loud what the eigenvector is. That's the same thing as saying v1 plus v2 is 0. So v1 equals minus v2, or v2 equals minus v1. 1 minus 1, minus 1, 1, any two opposite entries, non-zero, will form an eigenvector. Right, so pick the one solution, one equation. If I plug in 1 for v1, then obviously v2 will be minus 1. So the second eigenvector will be 1 minus 1. And therefore the general solution of the system is C1 eigenvector 1, 1 e to the 4t plus C2 1 minus 1, the other eigenvector, e to the minus 2t. I think this is one of the examples I also used last time in the previous lecture. So 1 minus 1 e to the minus 2t. So that's the general solution of the homogeneous system. So I want to take a moment here to describe the situation in which you have a single eigenvalue and 2 eigenvectors. This one happened actually in my class here. It's not an interesting system from my perspective if it's just 2 by 2. But the situation of a single eigenvalue with multiple eigenvectors is important to know that it exists if you solve larger systems. The reason it's not going to be that important, you will see it immediately. But it's important also to understand that if it appears in the 2 by 2 case, you don't have a different formula. Notice here it says either different eigenvalues and or different eigenvectors. So it implies that it's possible to have a single eigenvalue, but 2 different eigenvectors. Or to be more precise, an eigenspace of dimension 2 in which you actually have 2 different eigenvectors that describe the whole eigenspace when you solve for the eigenvector. So in that case, you still have 2 different independent solutions. Although the lambdas are the same, the V1 and V2 will not be the same. Will not be a multiple of each other, basically. So therefore, you still have 2 independent solutions that you need. So here is a typical example of a single eigenvalue and 2 eigenvectors. When we learn the geometry of solutions that you will see in the next lecture, that corresponds to what we're going to call a star node. So say the x prime is equal to 2x and y prime equals 2y. Now, if you write this in the matrix form as we normally do, the matrix of the system is 2, 0, 0, 2. And notice what happens if I try to find the eigenvector here. So lambda squared, the eigenvalue. So lambda squared minus the trace, which is 4, plus the determinant, which is also 4. So this gives me a single eigenvalue, which is 2 in this case. But notice what happens if I try to solve for the eigenvector. If I subtract 2 from the main diagonal, notice I don't have any condition on V1 and V2 because the matrix of the system is completely 0. This sometimes confuses students, like what's the solution? What is V1 or V2? Well, that's the point. It hits anything. Each equation is 0 equals 0. Any V1 and V2, any vector is an eigenvector. Okay, so in terms of vector spaces, how do you describe this eigenspace? How do you describe the entire collection of the eigenvectors corresponding to this eigenvalue? Well, you cannot describe it by a single eigenvector because it's not just a constant times a vector. It depends on 2 arbitrary constants. So you'll learn in 260 that you can easily extract the basis of the eigenspace by writing this vector as a linear combination of arbitrary constants. Scalars in this case, V1 or V2. So right off the bat, you have essentially 2 eigenvectors corresponding to lambda. Or again, the correct statement is the dimension of the eigenspace is 2 and 1, 0, 0, 1 is the basis of the eigenspace. So for the purpose of solving my differential system, I still have all I need basically, because when you look at the solutions of the form v bar e to the lambda t, I can produce 2 independent ones. I can produce 1, 0, e to the 2t, that's one solution. Let's write it actually in a linear combination, right? So c1, v1, e to the lambda t, and then plus c2, 0, 1, e to the lambda t is the same lambda, but the eigenvectors are different. Now, the reason why, so again, the same formula works in this case. The reason why this is not an interesting case in the 2 by 2 case, and you might notice already, if you combine this into a single vector, you have c1 times 1 e to the 2t plus 0. So the first unknown, the first component is c1 e to the 2t, and the second component c2 e to the 2t. So if you go back to the system over here, in the original, in the traditional form, in the original variables, you get that x of t is a constant e to the 2t, y of t is a constant e to the 2t. But this is the punchline. This is the punchline that I want you to pause and think about for a moment. Just go all the way back to this system that I started with, right? And as I mentioned here, we knew already, or you should know already, that x is a constant e to the 2t, y is a constant e to the 2t. Now, why you should know this already? Well, because this system is decoupled. Like, you can treat each equation separately. Normally, each equation depends on both x and y, in a system. But in this case, x prime depends on x only, y prime depends on y only. Nothing forces you to solve this via a system. You can solve each of them separately, and they happen to be the old-fashioned, the exponential ODE that I asked you guys to memorize. Okay, so x prime a constant times x, we know the solution is a constant e to the 2t. Y prime equals 2i, we know y is a constant e to the 2t, and that constant has nothing to do with the first one because the equations are decoupled. So we could simply solve them without going through the systems. But it's important to point out that the main theory of systems still applies here. And this formula still works. In this case, it's still the first case. Okay, single eigenvalue, but the dimension of the eigenspace is given by two different vectors. So this case won't happen too often in the homework, and I won't give it in the exam. But again, I want to point out why actually we have this and or v1 or not v2, because this could be equal, but this could still be different. The trouble is, of course, which comes next now. Not really the trouble, because we can fix it, but the different technique requires when you have a single eigenvalue, but the dimension of the eigenspace is still 1, so you have a single eigenvector. In that case, you are short of one independent solution. So you need to find a different way to provide the second independent solution. So that's going to be what comes next.